Welcome to an extraordinary journey through time and space, the story of how we discovered that Earth is not the center of the universe, but instead revolves around the sun. This is the story of bold thinkers, powerful discoveries, and a cosmic revolution that changed everything we thought we knew. Before we launch into this incredible tale, make sure to like and subscribe so you won't miss any future adventures in science and history. Now, dim the lights, get comfortable, and let your imagination soar beyond the stars. Sit back, relax, and prepare to explore the universe like never before. Let's begin. For most of human history, the cosmos was a mystery cloaked in myth and speculation. Long before telescopes, satellites, or space probes, ancient civilizations tried to make sense of the night sky. They watched the stars, the movements of the sun and moon, the changing seasons, and they began to build stories and systems to explain what they saw. The dominant belief in the ancient world was that Earth was the center of the universe. This idea, known as geocentrism, was not just a scientific model, it was a philosophical and religious assumption. To ancient peoples, it made perfect sense. The Earth felt solid and unmoving beneath their feet. The sun appeared to rise and set, the stars wheeled across the night sky, and no sensation of motion suggested that our planet was spinning or traveling through space. In ancient Mesopotamia, early astronomers tracked celestial cycles for agriculture and religious purposes. The Babylonians recorded star charts and developed mathematical models for predicting eclipses, but they did not yet challenge the idea of Earth's central position. The Egyptians and Chinese similarly viewed the heavens as a realm of divine order, often intertwined with the actions of gods and spirits. These cultures created elaborate cosmologies, but again, Earth was always at the center. It was the Greeks who began to think more critically about the structure of the cosmos. Pythagoras c. 570–495 BCE speculated that the Earth was a sphere based on the curved shadow it cast on the moon during a lunar eclipse. Later, Plato emphasized perfect geometric forms, encouraging the idea that heavenly bodies must move in perfect circles. But the most influential Greek thinker in this story was Aristotle 384–322 BCE. He proposed a model of the universe with Earth at the center, surrounded by concentric spheres carrying the moon, sun, planets, and stars. Everything in the heavens, he believed, was perfect and unchanging, made of a fifth element, ether. Aristotle's geocentric model was elegant, philosophical, and deeply persuasive. Centuries later, Claudius Ptolemy c. 170 CE expanded on Aristotle's ideas in his great work, the Almagest. Ptolemy created a complex system of epicycles, small circles moving on larger circles, to account for the strange paths of the planets, especially their apparent backward motion, retrograde motion. This mathematical model, though flawed, was remarkably good at predicting planetary positions. The Ptolemaic system became the standard for over 1,400 years. It was adopted by the Islamic world during the golden age of Islamic science, and later by medieval Europe. It aligned with religious teachings, especially in Christianity, which placed humanity, and by extension, Earth at the center of God's creation. By the 15th century, the geocentric model wasn't just a theory, it was reality, backed by the best science of the time, supported by religious doctrine, and reinforced by everyday experience. To question it was to question the natural order itself. But not everyone was satisfied. A quiet revolution was about to begin. In the next chapter, we'll meet the man who dared to place the sun, not the Earth, at the center. For nearly 1,500 years, the geocentric model reigned supreme. It placed Earth immobile at the center of the universe, with the moon, sun, stars, and planets circling around it in perfectly ordered spheres. This model, formalized by Ptolemy in the 2nd century CE, was deeply embedded not only in scientific thought, but in philosophy, theology, and culture. It was elegant, orderly, and wrong. In the early 16th century, a quiet but revolutionary idea began to take shape in the mind of a man who would forever alter humanity's perception of its place in the cosmos. His name was Nicolaus Copernicus. A scholar in isolation, Copernicus was born in 1473 in the town of Torun, in what is now Poland. Orphaned at a young age, he was raised by his uncle, a powerful bishop in the Catholic Church. This familial connection gave Copernicus access to a solid education and, importantly, a degree of protection, an invaluable asset for someone who would later challenge one of the most entrenched ideas of his time. He studied a wide range of disciplines, mathematics, astronomy, law, medicine, and theology. At the University of Krakow, he was introduced to the problems of Ptolemaic astronomy. Even then, he found aspects of the Earth-centered model troubling, not morally or theologically, but mathematically. It was complicated, awkward, and full of ad hoc adjustments. In the Ptolemaic system, planets had to move in epicycles, small circles along larger circles, to account for their observed motion in the sky. It worked well enough to make predictions, but it felt forced, more like patchwork than truth. Copernicus began to wonder, what if the whole system was wrong? The seeds of revolution. It's important to understand that Copernicus wasn't the first to suggest a sun-centered universe. Ancient Greek astronomer Aristarchus of Samos, centuries before, had proposed a heliocentric model. But Aristarchus was ahead of his time, and his ideas didn't take hold. What made Copernicus different was that he developed a comprehensive mathematical model, something no one else had done in such detail. Around 1514, Copernicus began circulating a short manuscript called the Commentariolus to a small circle of trusted colleagues. In it, he laid out the basic idea: the Earth orbits the Sun. This was more than just a new astronomical model, it was a philosophical earthquake. If Earth moved, it was not the fixed center of the universe. If it spun on its axis, the entire vault of heaven was no longer rotating above us each day. And if the planets, including Earth, orbited the Sun, then we were just one of several wandering bodies in a vast cosmos. It was an idea that could shake not only science, but the worldview of an entire civilization. The heliocentric model explained. So what exactly did Copernicus propose? In his model, the Sun is at the center of the universe, motionless. The Earth rotates on its axis once every 24 hours, explaining the daily rising and setting of the stars and Sun. The Earth revolves around the Sun once a year. The Moon orbits Earth, just as before. The other planets also orbit the Sun, in order of increasing distance: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. This simple restructuring immediately explained several puzzles of the geocentric model. Most notably, it made sense of retrograde motion, the occasional backward movement of planets in the sky. In the Ptolemaic model, retrograde motion required epicycles. In Copernicus's model, it was a natural illusion caused by Earth overtaking another planet in its orbit. Copernicus's system also explained the changing brightness of planets like Mars and Venus, something the geocentric model struggled with. Yet, despite its elegance, the Copernican model didn't have all the answers. Like Ptolemy, Copernicus still insisted that orbits were perfect circles, which they aren't. This meant his system still required some minor adjustments, though far fewer than the older one. The full mathematical simplicity wouldn't emerge until later, with Kepler's elliptical orbits. Still, the core insight was revolutionary. The Earth was not the center, the heavens did not revolve around us, delaying the storm. So why didn't Copernicus rush to publish his ideas? The answer lies in his character. Copernicus was cautious, perhaps even fearful. He was no firebrand, no Galileo. He knew his theory would challenge powerful institutions. The Church, which had long used Aristotelian cosmology to support its theology, might see his ideas as heresy. More than that, Copernicus wasn't seeking controversy. He wanted to reform astronomy, not overturn society. He worked on his magnum opus for decades, a book called De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres. He hesitated to publish it, even as he grew old. It wasn't until 1543, the year of his death, that the book was finally printed, possibly placed into his hands on his deathbed. It was dedicated to Pope Paul III, in an attempt to shield it from theological backlash. Ironically, De Revolutionibus was initially met with interest, not outrage. Most scholars treated it as a useful mathematical tool, a way to calculate planetary positions, rather than a literal description of reality. The book was dense, technical, and hard to read. For many, it was easier to ignore the implications, but not for long. As younger scientists took notice, especially in the following century, Copernicus's model would become the cornerstone of a revolution, ripples across time. The Copernican revolution didn't erupt all at once. It began slowly, like a shift in the wind, but it grew over time. In the decades following Copernicus's death, astronomers began testing, refining, and debating his ideas. Some tried to merge the old and new systems. Others challenged his assumptions, but gradually, his central insight, that Earth was in motion, gained traction. His model laid the foundation for Tycho Brahe's precise measurements, Kepler's laws of planetary motion, Galileo's telescopic observations, and Newton's universal laws of physics. Each of these developments depended on Copernicus's courage to think differently. He didn't have a telescope. He didn't see planets in motion with his own eyes. He didn't even fully understand gravity, but he saw what others missed, a simpler, more coherent way to explain the heavens. He trusted mathematics, he trusted reason, and he believed that the universe, while complex, could be understood by the human mind. In doing so, Copernicus began the process of decentering humanity from the cosmos and placing us instead within it. The spark that Copernicus lit in the 16th century did not immediately ignite a fire. His heliocentric model was bold, elegant, and mathematically sound, but it lacked physical proof. There were still major objections: philosophical, theological, and observational. If the Earth moved, why didn't people feel it? Why wasn't there any observed shift in the stars, known as stellar parallax? And if his model was so clean, why did his predictions still require strange circular tweaks? For the Copernican model to truly take hold, it needed precision, observations so accurate they could confirm or disprove its fundamental claims. It also needed refinement. Circular orbits, the holdover from ancient ideas of perfection, didn't match reality. The universe wasn't just poetic, it was mathematical. Enter two of the most brilliant minds of the scientific revolution, Tycho Brahe and Johannes Kepler, unlikely partners in an unlikely collaboration that bridged the gap between old and new. Tycho Brahe. The last of the naked-eye astronomers, Tycho Brahe, who was born into Danish nobility in 1546, wealthy, eccentric, and obsessively curious, Tycho's passion for astronomy began at a young age. At a time when astronomy was more philosophy than science, Tycho brought something radical to the field: data. In 1572, a supernova appeared in the night sky, a new star, in a supposedly unchanging celestial sphere. Tycho carefully observed and recorded it, showing that this brilliant light was far beyond the moon. This shattered the ancient belief that the heavens were fixed and perfect. It also made Tycho famous. Soon he persuaded King Frederick II of Denmark to fund the construction of Uraniborg, a state-of-the-art observatory. There, for more than 20 years, Tycho recorded the movements of planets and stars with unprecedented accuracy, all without a telescope, which hadn't yet been invented. His planetary data was the most precise the world had ever seen, accurate to within a minute of arc, a level of detail that would prove crucial. But Tycho didn't fully embrace Copernicus. Instead, he proposed a compromise, the Tychonic model. In this hybrid system, Earth remained at the center, unmoving. The Sun orbited the Earth. All the other planets orbited the Sun. To Tycho, it preserved the stability of Earth and the theological order of creation, while still accounting for the observational advantages of Copernicus's theory. It was a strange model, but one that offered a bridge between ancient authority and new evidence. And yet, Tycho's greatest contribution wasn't his model, it was his data. And for that data to reveal its secrets, it needed a new kind of mind, not just a mathematician, but a visionary. That mind belonged to Johannes Kepler. Johannes Kepler, a mind of fire and faith born in 1571 in Germany, Kepler came from a very different world. He was poor, sickly, and deeply religious, obsessed with finding the mathematical harmony of God's creation. To Kepler, the universe wasn't just a physical system, it was a divine architecture, built on geometric and musical principles. Kepler was a Copernican from the start. He believed that the sun belonged at the center, and he searched for the hidden mathematical order behind the cosmos. In 1600, Kepler joined Tycho in Prague, just a year before Tycho's death. Their partnership was uneasy. Tycho was proud and secretive, Kepler intense and idealistic. But when Tycho died in 1601, Kepler inherited his life's work, the most accurate astronomical observations ever made. With this treasure trove of data in hand, Kepler set out to solve one of astronomy's great mysteries, the orbit of Mars. Copernicus's model still relied on circular orbits with small corrective epicycles, but Mars refused to fit those circles. Kepler tried every combination, every correction. For years he struggled, searching for the hidden pattern. Then, in a stunning moment of insight, Kepler did something no one had dared before. He abandoned the circle, ellipses, and the laws of planetary motion. Kepler discovered that planets move not in circles, but in ellipses, flattened ovals, with the Sun at one of the two foci. This was radical. For 2,000 years, the circle had been sacred in astronomy, considered the perfect form, suitable for the heavens. But the data didn't lie. The orbit of Mars, when mapped against Tycho's measurements, only fit an ellipse. This breakthrough led Kepler to formulate what would become known as his three laws of planetary motion. Elliptical orbits. Planets move in ellipses, with the Sun at one focus. Equal areas in equal times. A planet sweeps out equal areas in its orbit in equal intervals of time, meaning it moves faster when closer to the Sun and slower when farther away. Harmonic law. The square of a planet's orbital period is proportional to the cube of its average distance from the Sun. These laws weren't just useful, they were true. They explained not only why the planets moved as they did, but also predicted their motions with incredible accuracy. For the first time, astronomy was not a tangled web of circles, but a clean, lawful system rooted in mathematics and observation. The turning of the tide. Kepler's work, particularly his publication of the Astronomia Nova in 1609, marked a turning point. The heliocentric model was no longer just a theoretical framework. It was now quantitatively accurate, predictive, and grounded in real-world data. The Copernican system had found its precision. The orbits were not only plausible, but beautifully explainable through physical laws. Still, resistance remained. Kepler's laws implied that Earth was just one of many planets obeying the same rules, a staggering shift in worldview. Yet the momentum was building. What Tycho had measured, Kepler had explained, but there was still something missing. Proof that the Earth itself was in motion, and that the planets indeed circled the Sun as Kepler described. That proof would come through the eyes of another genius, with a telescope. A bridge to Galileo. Kepler died in 1630, never knowing that his laws would later help Isaac Newton derive the universal law of gravitation. Nor did he live to see how his elliptical orbits would become standard in astronomy. But Kepler, driven by a mystical belief in harmony and a rigorous dedication to data, accomplished something extraordinary. He married precision and imagination. He gave shape to the solar system, and together with Tycho Brahe, one a patient observer, the other a relentless theorist, they helped move science from the Earth-centered past into a sun-centered future. The story of the heliocentric theory is filled with bold ideas and brilliant minds. Copernicus reimagined the structure of the cosmos. Tycho Brahe measured the heavens with unmatched precision. Kepler deciphered the planets' elliptical paths. But one man would bring the stars down to Earth, Galileo Galilei, and in doing so, ignite a confrontation between science and authority that would echo through the centuries. The Renaissance mind Galileo was born in Pisa, Italy, in 1564, the same year as Shakespeare, and just a few years after Copernicus's death. A mathematician, physicist, engineer, and philosopher, Galileo embodied the restless curiosity of the Renaissance. He believed the universe could be understood not through ancient texts or divine revelation, but through observation, experimentation, and mathematics. In his early career, Galileo made significant advances in mechanics, studying the motion of falling bodies, pendulums, and inclined planes. He showed that objects of different weights fall at the same rate, challenging the teachings of Aristotle. But his most important contributions would come when he turned his gaze to the sky. A new instrument in 1609, Galileo heard of a strange device from the Netherlands, a tube with lenses that could make distant objects appear closer. It was called a spyglass, or telescope. Galileo didn't invent it, but he improved it greatly. Within months, he had built a telescope powerful enough to magnify the heavens by a factor of 20. It wasn't perfect, the lenses were crude, and the view often blurry, but it was revolutionary. For the first time in human history, the sky could be studied in detail, and what Galileo saw through his telescope would shake the foundations of the old world, shattering the heavens. In 1610, Galileo published his findings in a short book titled Sidereus Nuncius, the Starry Messenger. It was part scientific report, part poetic proclamation. Through his telescope, Galileo saw the moon's surface pockmarked with craters and mountains, not smooth and perfect, as Aristotle had claimed. Countless stars in the Milky Way, far more than the naked eye could see. 4 stars orbiting Jupiter, which he quickly realized were moons now known as the Galilean moons, Io, Europa, Ganymede, and Callisto. This last observation was particularly significant. It provided the first direct evidence that not all celestial bodies orbit the Earth. Jupiter had its own miniature system, a solar system in miniature, clearly visible in the night sky. If moons could orbit another planet, then perhaps not everything needed to revolve around Earth. Galileo had found a mechanical counterexample to geocentrism. Then came another revelation, the phases of Venus. In 1610, Galileo observed that Venus went through a full cycle of phases, just like the moon. This could not happen if Venus orbited Earth, but it made perfect sense if Venus orbited the Sun. This single observation provided irrefutable proof that at least part of the solar system was heliocentric. The evidence was mounting, and Galileo knew it. Champion of Copernicus. By this point, Galileo had become a public intellectual, a celebrity scientist. He lectured, debated, and published widely. Unlike Kepler, who was more private and mathematical in his arguments, Galileo was passionate and confrontational. He wanted not just to demonstrate heliocentrism, but to convince the world of its truth. In 1613, he wrote a letter to the Grand Duchess Christina of Tuscany, arguing that science and scripture could coexist, but that the Bible was not meant to be a science textbook. Quoting a church father, he wrote, "The Bible tells us how to go to heaven, not how the heavens go." Galileo's tone and ideas began to attract criticism. At the time, the Catholic Church had not yet taken an official stance against Copernicanism, but many of its leaders were wary. Heliocentrism contradicted the geocentric implications of Scripture and challenged centuries of established authority. In 1616, the Church responded. It declared heliocentrism to be formally heretical and placed Copernicus's De Revolutionibus on the Index of Forbidden Books, pending correction. Galileo was warned not to defend or teach the theory as truth. For a while, he remained quiet. The dialogue that sparked a trial in 1623. Galileo's fortunes seemed to improve. A friend and admirer, Cardinal Maffeo Barberini, became Pope Urban VIII. Encouraged, Galileo returned to the subject that had consumed his life. In 1632, he published his most famous and most controversial work, Dialogue Concerning the Two Chief World Systems. Presented as a conversation between 3 characters, Salviati, a Copernican, Simplicio, a defender of geocentrism, and Sagredo, a neutral observer. The book cleverly argued for heliocentrism, but it didn't just explain the science, it mocked the old system. Worse still, the geocentric character, Simplicio, was made to sound foolish, naive, slow-witted and stubborn. Many readers saw Simplicio as a thinly veiled caricature of the Pope himself. Galileo had gone too far. The Church launched an investigation. Galileo was summoned to Rome in 1633 and tried by the Roman Inquisition. He was found guilty of vehement suspicion of heresy. Though spared torture and execution, Galileo was forced to recant his views. He was placed under house arrest for the rest of his life. According to legend, after recanting, he muttered, "Eppur si move, and yet it moves." Whether or not he said it, the phrase captured the essence of the conflict: the truth does not bend to authority. A legacy that moved the world. Galileo spent his final years writing, studying motion and physics. His work on falling bodies and inertia would later influence Newton. Though silenced, his ideas were already out in the world, and they would never be contained again. His telescope had shown that the universe was not what the ancients imagined. His courage had shown that truth could survive, even under pressure, and his science had laid the groundwork for the modern method: observe, measure, test, and question. Galileo's trial became a defining moment in the history of science, a symbol of the struggle between dogma and evidence, authority and inquiry. More than any other figure, Galileo brought the heliocentric theory from the realm of mathematics into the realm of empirical reality. His observations showed that Copernicus was not just a theorist, but a prophet of modern science. In time, the Church would acknowledge its mistake. In 1992, more than 350 years after the trial, Pope John Paul II formally expressed regret for Galileo's condemnation. But Galileo's true vindication had come long before. It came with every discovery that followed, every scientist who built upon his work, every satellite that launched into orbit, and every child who looked through a telescope in wonder. He taught us not just how the heavens go, but how we might come to understand them. The story of the heliocentric theory is not just a tale of telescopes, planets, and mathematical insight. It is also a story of institutions, particularly one of the most powerful and enduring in human history, the Catholic Church. To understand why the heliocentric model was so controversial, and why figures like Copernicus, Kepler, and Galileo faced such resistance, we need to look beyond the stars, to the cultural, religious, and political context of their time. This is the story of how science challenged authority, and how that authority pushed back. The medieval cosmos, in the centuries leading up to the Renaissance, Europe's understanding of the cosmos was shaped almost entirely by the teachings of Aristotle and Ptolemy, interpreted and protected by church doctrine. In this worldview, the earth was fixed and unmoving at the center of the universe. The heavens were perfect, eternal, and unchanging. The celestial spheres, vast, transparent orbs, carried the moon, sun, stars, and planets in perfect circular paths around the earth. This model wasn't just scientific, it was theological. Earth's position at the center symbolized humanity's importance in the divine plan. The heavens, pure and orderly, represented the realm of God. To question this arrangement was to question not only the natural order, but the very structure of creation itself. By the Middle Ages, the Ptolemaic system had become embedded in Christian cosmology. The idea of a geocentric universe was reinforced in religious teachings, sermons, and interpretations of Scripture. Key biblical passages seem to affirm a stationary earth. The world is firmly established, it shall never be moved. Psalm 104:5. The sun rises and the sun goes down, and hurries back to where it rises. Ecclesiastes 1:5. To church leaders, these were not poetic metaphors, they were evidence. And when Copernicus introduced his heliocentric model, it wasn't just a scientific challenge, it was perceived as a spiritual threat. Copernicus and caution. When Copernicus released De Revolutionibus Orbium Coelestium in 1543, it was dedicated to Pope Paul III. Copernicus hoped to win the Church's support, not provoke its opposition. He presented his model as a mathematical tool, a useful way to calculate planetary motions, not necessarily a literal truth. For several decades, the book circulated quietly, used by astronomers and scholars without much controversy. After all, it was dense, technical, and written in Latin. It didn't spark mass upheaval, but that began to change. As figures like Kepler, and especially Galileo, took up the Copernican model and treated it as physical reality, not just a model, the Church grew increasingly uneasy. The Reformation and the Counter-Reformation. To understand this shift, we must consider the timing. The 16th century wasn't just the age of astronomy, it was the age of religious turmoil. In 1517, Martin Luther had nailed his 95 Theses to the church door in Wittenberg, launching the Protestant Reformation. Across Europe, religious authority fractured. Catholicism faced its greatest challenge in centuries. In response, the Church initiated the Counter-Reformation, a sweeping movement to reaffirm Catholic doctrine and reassert control over intellectual life. This meant tighter censorship, greater scrutiny of new ideas, and a more rigid alignment between science and Scripture. In this climate, heliocentrism became politically dangerous. It wasn't just a scientific theory anymore. It became a symbol of defiance, an emblem of the Protestant emphasis on personal interpretation over institutional authority. Even though many early Protestants also rejected heliocentrism, the idea that the Bible should not dictate scientific thought aligned closely with Protestant thinking. The Church felt besieged, and when Galileo stepped forward with powerful observations and passionate arguments, it saw not just an astronomer, but a challenge to its authority. The Index and the Inquisition. In 1616, the Church officially responded to the growing popularity of heliocentrism. The Congregation of the Index declared the heliocentric model to be formally heretical because it contradicted the literal interpretation of Scripture. Two key actions were taken. Copernicus's book was suspended until corrected, specifically, until its language was softened to present heliocentrism as a hypothesis. Galileo was warned not to defend or teach heliocentrism as fact. This was not yet a full persecution, but it marked a hardening of the Church's stance. Galileo's later trial in 1633 was the culmination of years of rising tension. When Galileo published his dialogue concerning the two chief world systems, portraying heliocentrism as truth and mocking its critics, it was seen as a direct affront to the Church's warnings. He was tried by the Roman Inquisition, found guilty of vehement suspicion of heresy, and forced to recant. His book was banned. He was placed under house arrest for the rest of his life. Beyond Galileo, suppression and survival. Even after Galileo, the Church continued to resist heliocentrism. The ban on Copernicus's work remained in place for decades. Heliocentric texts were censored or banned, and Catholic astronomers had to be cautious in how they discussed celestial models. Yet the theory continued to spread. Protestant regions, especially in Northern Europe, became centers for Copernican thought. Kepler's laws gained traction. Newton's discoveries later made heliocentrism mathematically unassailable. By the late 1600s, even within Catholic circles, it became increasingly difficult to deny the reality of the sun-centered system. Eventually, the Church quietly retreated. In 1822, the Vatican officially allowed the publication of books treating heliocentrism as fact. In 1835, Galileo's dialogue was finally removed from the Index of Forbidden Books, and in 1992, over 3.5 centuries after Galileo's trial, Pope John Paul II formally acknowledged the Church's error, praising Galileo as a brilliant physicist who suffered unjustly. The lesson of resistance. The Church's resistance to heliocentrism is often painted as a battle between science and religion, but it was also about power, interpretation, and the growing pains of a world moving into modernity. The Church had long served as the gatekeeper of knowledge. The heliocentric model was not just a threat to theology, it was a threat to the Church's role as the arbiter of truth. The Galileo affair became a symbol of this struggle, the cost of defending a rigid worldview in the face of growing evidence. It serves as a cautionary tale about the dangers of silencing inquiry and confusing authority with certainty. And yet the story is more complex than villains and victims. Many within the Church were deeply committed to learning. Jesuit astronomers made important contributions to science. Some Church officials admired Galileo, but were constrained by the politics of the time. In the end, the heliocentric theory survived not because it was easy, but because it was true. And truth, once seen, is hard to unsee. The universe had changed, not just in the heavens, but here on Earth. A new era was dawning, an age where evidence would increasingly challenge belief, and where the cosmos was no longer a tidy hierarchy with Earth at its heart, but a vast unfolding reality governed by laws yet to be discovered. By the late 17th century, the heliocentric model was gaining acceptance. The observations of Galileo, the laws of planetary motion discovered by Kepler, and the mounting inadequacy of the geocentric model had tipped the balance. But one question still lingered, perhaps the most important of all. Why do the planets move as they do? Why do they orbit in ellipses, not circles? What force keeps them bound to the sun? What invisible rule governs their motion? Enter Sir Isaac Newton, a man who would answer not just that question, but in doing so, rewrite the laws of the universe. The birth of a genius. Isaac Newton was born in 1642 in Woolsthorpe, England, the same year that Galileo died. Raised by his grandmother after his father's death, and abandoned by his mother, Newton was an intense, solitary, and obsessively curious child. He studied at Trinity College, Cambridge, where he immersed himself in mathematics, optics, alchemy, and astronomy. A student of the new science, he devoured the works of Descartes, Kepler, and Galileo. But Newton didn't just absorb ideas, he transformed them. In his early 20s, while Cambridge was closed due to the Great Plague of 1665, Newton returned home. There, in what he later called his Year of Wonders, he laid the groundwork for calculus, developed his theories on light and color, and began to explore the nature of gravity. Legend says an apple fell from a tree and inspired him. Whether true or not, Newton's insight would revolutionize physics and validate heliocentrism beyond any doubt. Kepler's laws revisited. Before Newton, Johannes Kepler had formulated 3 laws of planetary motion: elliptical orbits with the sun at one focus. Planets sweep out equal areas in equal times. The square of a planet's orbital period is proportional to the cube of its average distance from the sun. These laws beautifully described how planets moved, but they didn't explain why. There was no physical mechanism tying planets to the sun. What Newton realized was that there must be a universal force acting between the sun and the planets, just as there is a force that pulls objects to the ground on Earth. He asked the revolutionary question, could it be the same force? The universal law of gravitation. In 1687, Newton published his most famous work, Philosophia Naturalis Principia Mathematica, commonly known as the Principia. In it he presented his law of universal gravitation. Every particle in the universe attracts every other particle with a force that is directly proportional to their masses and inversely proportional to the square of the distance between them. In other words, the same force that pulls an apple to the ground also pulls the moon toward the Earth, and the Earth toward the sun. This single law unified celestial and terrestrial mechanics for the first time. The heavens and the Earth were not separate realms, as Aristotle had claimed. They were part of one universe, governed by the same physics. Using this law, Newton derived Kepler's laws from first principles. He showed that elliptical orbits were not mere coincidence. They were the natural result of gravitational attraction, inertia, motion, and the clockwork universe. In addition to gravity, Newton laid out his famous 3 laws of motion. An object remains at rest or in uniform motion, unless acted upon by a force. Force equals mass times acceleration, F equals sine ma. For every action, there is an equal and opposite reaction. These laws became the foundation of classical mechanics. They explained how objects moved, how forces interacted, and how planets, moons, and comets behaved. The solar system, once a divine mystery, was now a mechanical system, a grand cosmic clock whose workings could be predicted and understood. To Newton, God was the architect of this system, and his laws were the blueprint. The universe was no longer a theater of unpredictable divine interventions. It was governed by order, precision, and mathematical beauty. From theory to triumph, the Principia was a landmark achievement. Newton had done what Copernicus, Galileo, and Kepler could not. He explained why the heliocentric system worked, and he did it with math, logic, and evidence. The scientific community was stunned. Even skeptics had to admit the heliocentric theory was now not only observationally plausible, it was physically inevitable. Perhaps the most stunning demonstration came with the prediction and explanation of tides. Newton showed that the moon's gravitational pull caused the ocean tides, something no earlier model could fully explain. And when Halley's comet returned, just as predicted using Newton's equations, the world had to take notice. The heliocentric theory was no longer just a hypothesis. It had become a law-governed reality. Newton's legacy, Isaac Newton, became a towering figure, not just in science, but in the history of ideas. His vision of the universe as a rational, law-bound system reshaped every field it touched, from astronomy to engineering to philosophy. Voltaire, who helped popularize Newton's ideas in France, declared, "Newton explained the motion of the universe. He discovered the laws of nature." Einstein would later write, "Nature to Newton was an open book, whose letters he could read without effort." The heliocentric theory had come a long way, from Copernicus's daring proposal, through Galileo's telescope and trial, to Newton's majestic synthesis of motion and gravity. Thanks to Newton, the sun-centered universe wasn't just an idea, it was a demonstrated reality, grounded in mathematics and confirmed by observation. And with it came a new confidence that the universe was knowable, that nature followed rules, and that humans, through reason, could uncover them. The world would never be the same. The heliocentric model, by the start of the 18th century, was no longer a controversial theory. It was the scientific consensus. But the impact of this cosmic reorientation extended far beyond astronomy. It reshaped philosophy, religion, politics, and education. The revolution started by Copernicus and solidified by Newton helped give rise to a new era, the Age of Enlightenment. This was the age of reason, an age where the universe was no longer seen as unknowable or mystical, but as something that could be studied, understood, and explained by human intellect. The mind of man awakens. The Enlightenment, spanning from the late 17th to the early 19th century, was a sweeping intellectual movement across Europe and its colonies. Its thinkers believed in rationality over superstition, science over dogma, observation over tradition, inquiry over obedience. They argued that humans could improve society and their own lives through knowledge and critical thinking. At the heart of this belief was the model of nature revealed by Newtonian physics and the heliocentric universe. The sun no longer revolved around us. We revolved around it. That simple shift had radical consequences. It suggested that truth was not dictated by authority, but discovered through investigation. As poet Alexander Pope wrote, "Nature and nature's laws lay hid in night. God said, 'Let Newton be,' and all was light." The cosmos as a clock. The Enlightenment adored Newton's vision of the universe, a giant mechanical clock governed by fixed, universal laws. Gravity was no longer magic. Motion was no longer mysterious. The cosmos ticked with precision, like a machine. Philosophers such as Voltaire, Locke, and Kant were inspired. Newton's Principia wasn't just a physics book, it became a symbol of rational order. Voltaire famously introduced Newton's ideas to France and celebrated them as a triumph of reason. To many Enlightenment thinkers, Newton's laws confirmed that nature was comprehensible, that the same mind which deciphered the skies could also reform politics, religion, and society. The belief took hold that reason and evidence could guide everything, from how we build governments to how we understand the soul, rewriting the relationship between science and religion. The heliocentric theory also transformed the dialogue between science and religion. In the Middle Ages, truth was revealed through scripture and tradition. In the Enlightenment, truth could be observed, tested, and reasoned. This didn't necessarily destroy religious faith, but it redefined it. Some thinkers became deists. They believed in a creator, but not one who intervened in human affairs. To them, God was like a cosmic watchmaker, who built the universe with perfect laws and let it run on its own. Others saw no need for the divine at all. The success of heliocentrism and the predictability it implied suggested that perhaps everything in nature, even life and mind, could be explained without supernatural causes. It was a seismic shift. The sacred was no longer the only lens through which to view the universe. Science had carved out its own authority. Education, publishing, and public knowledge. With the Enlightenment came an explosion in books, journals, lectures, and encyclopedias. Scientific knowledge, once confined to universities or the church, became increasingly public. Institutions such as the Royal Society of London, the Académie des Sciences in Paris, and dozens of observatories across Europe helped bring science into the public sphere. Literacy grew. Access to telescopes and charts spread. People began to understand that the Earth moved, the stars were suns, and the universe was vast. This era saw the first popular science books. Diagrams of the heliocentric system were printed in newspapers. School children learned about the solar system, not as a theory, but as fact. Heliocentrism became common knowledge, as familiar as the rising sun, cosmic humility. There was also a new emotional tone to science, a blend of awe and humility. The Copernican model had removed Earth from the center of the cosmos, but Enlightenment thinkers saw this not as a demotion, but as an opportunity. The universe was far larger than imagined. The stars were not fixed lights on a crystal sphere, they were other suns, possibly with planets of their own. The cosmos was not a stage set for humanity, but an expansive, intricate structure beyond comprehension. The philosopher Immanuel Kant even speculated about island universes, what we now call galaxies. It was an extraordinary realization. Earth was just a speck, orbiting an ordinary star, in one corner of a vast, possibly infinite cosmos. This perspective seeded what we now call cosmic humility, the idea that we are not the center of creation, but rather a part of something far bigger and possibly more beautiful than we can fully grasp. Revolution on Earth. Just as heliocentrism had disrupted cosmic order, Enlightenment thinkers used its principles to challenge earthly authority as well. If the universe obeyed natural laws, why shouldn't human society? Why should kings rule by divine right, or churches dictate truth? From the American Revolution to the French Revolution, the Enlightenment's ideals, fueled by the same rationalism that proved heliocentrism, drove people to rethink government, liberty, and justice. Science had changed our view of the skies, and now it was changing the world below. The legacy of Enlightenment and the heliocentric idea. By the close of the 18th century, the heliocentric theory was no longer a rebellion. It was a foundation. It had transformed from heresy to orthodoxy, from dangerous idea to educational standard. More importantly, it had become a model of inquiry, a way of thinking that prized evidence over dogma, calculation over guesswork, and discovery over obedience. The earth moves, the sun shines not for us alone, and we, through patient observation and reason, had figured it out. This idea that humans could uncover the workings of the universe through their own minds was perhaps the Enlightenment's greatest gift. The heliocentric theory was not just a victory for astronomy, it was a triumph for humanity. By the dawn of the 19th century, the heliocentric theory was firmly established. The sun was recognized as the center of our solar system, and Newton's laws explained the motions of the planets with remarkable precision. But the story of our understanding of the cosmos was far from over. The centuries that followed brought astonishing discoveries that expanded the heliocentric model, revealing that our solar system is just a tiny part of a vast dynamic universe. Charting the solar system. In the 1800s, astronomers began to explore the solar system in more detail. Telescopes improved dramatically, allowing scientists to discover new planets and objects. In 1781, William Herschel discovered Uranus, the first planet found since antiquity. The search for a missing planet between Mars and Jupiter led to the discovery of the asteroid belt. Later, Neptune was discovered in 1846 through mathematical prediction based on irregularities in Uranus's orbit. In the 20th century, Pluto was discovered in 1930, though it was later reclassified as a dwarf planet. These discoveries expanded the solar system beyond the classical 7 planets known to the ancients, showing it to be far larger and more complex. The birth of astrophysics, with advances in spectroscopy and photography, scientists began to study not just the positions of celestial objects, but their composition and behavior. They learned that the sun is a star, a massive ball of burning gas, primarily hydrogen and helium. Other stars scattered across the night sky were also suns, many with planets of their own. This opened the door to astrophysics, the study of the physical properties and life cycles of stars, planets, and galaxies. The heliocentric model, while still central, was now seen as part of a grander cosmic structure, Galileo's legacy and beyond. Though Galileo was the first to use a telescope for astronomy, the technology evolved dramatically. By the late 19th and early 20th centuries, astronomers were building larger and more powerful telescopes, reaching further into space. Edwin Hubble, working in the 1920s, made one of the most groundbreaking discoveries of all, the realization that the nebulae observed in the sky were actually entire galaxies, far beyond our own Milky Way. He also discovered that the universe is expanding, that galaxies are moving away from each other, implying that the cosmos had a beginning, later known as the Big Bang. From a solar system to a universe, this expanded our cosmic perspective dramatically. Earth is not the center of the universe. The sun is one star among billions in the Milky Way. The Milky Way itself is one galaxy among billions in the observable universe. The heliocentric model had been the first step in dethroning Earth from cosmic centrality, but modern astronomy showed that Earth's position is truly humble. Our solar system is a small part of a vast, dynamic, and constantly evolving cosmos. Space exploration, making the universe tangible. The 20th century also saw humanity's first physical journeys beyond Earth, starting with satellites, then robotic probes, and eventually human missions to the Moon. We began to explore our solar system firsthand. Probes sent to Mars, Jupiter, Saturn, and beyond have sent back detailed data about planets, moons, and other objects, confirming and expanding our understanding of the heliocentric system. Space exploration transformed the heliocentric model from abstract theory to living reality, a system we can now navigate and study directly. Modern challenges and new horizons. Even today, the heliocentric theory is not the final word. Astronomers investigate how our solar system formed and evolved, the possibility of life on other planets, the nature of dark matter and dark energy shaping the cosmos, the precise dynamics of planets around other stars, exoplanets. The tools and knowledge keep advancing. New telescopes like the James Webb Space Telescope peer deeper into space and further back in time. Science has taken us far from the Earth-centered cosmos, yet every discovery confirms the fundamental truth that the Earth and the planets orbit the Sun. The continuing journey, the heliocentric theory, was a monumental leap in human understanding. It transformed our worldview, our culture, and our place in the universe. but it was only the beginning. As we look to the stars, chart new worlds, and seek answers to the deepest cosmic mysteries, we continue the journey that began with Copernicus, Galileo, and Newton. A journey fueled by curiosity, guided by reason, and grounded in the humble realization that the universe is vast, complex, and infinitely fascinating. The heliocentric theory, which once challenged centuries of established belief, has now become an integral part of how we understand our world and our place in the cosmos. From classrooms to cutting-edge research labs, from popular culture to philosophical debates, the idea that Earth and the other planets orbit the Sun shapes how we think, learn, and imagine the universe. Science. The foundation of modern astronomy today, heliocentrism is the foundation of modern astronomy and space science. It informs everything from the basic teaching of the solar system to the planning of space missions. Thanks to centuries of scientific progress, we now know the detailed orbits of planets, moons, asteroids, and comets, the forces that govern their motion, including gravity and electromagnetic effects, how the solar system formed from a cloud of gas and dust billions of years ago, the existence of thousands of planets orbiting other stars, expanding our concept of planetary systems beyond our own. Modern telescopes, satellites, and space probes rely on the principles of heliocentrism to navigate and explore. Without this framework, space travel as we know it would be impossible. Education. Teaching the universe in schools around the world, students learn the heliocentric model early in their science education. It is often one of the first lessons that introduces children to scientific thinking, the process of observation, hypothesis, testing, and acceptance of evidence. The story of heliocentrism, from Copernicus's bold proposal, Galileo's telescopic observations, to Newton's laws, is a powerful example of how knowledge evolves. It teaches critical lessons, that ideas must be tested against evidence, that scientific truths can challenge tradition, that the universe is understandable through reason. Culture. From revolution to inspiration, the heliocentric theory has also deeply influenced culture, art, literature, philosophy, and religion. In the arts, the shift from Earth-centered to Sun-centered cosmos inspired new ways of thinking about humanity's place in the universe. It appeared in paintings, poems, and novels, exploring themes of discovery, humility, and progress. Philosophers debated its implications for free will, spirituality, and human significance. Was Earth still special? Did humans still have meaning in such a vast cosmos? Religious institutions had to wrestle with these changes. While some resisted, others adapted, finding ways to reconcile faith with scientific understanding. The heliocentric theory and modern worldviews today, the heliocentric model is more than a scientific fact. It's a symbol of the scientific method and the power of human reason. It reminds us that our assumptions can be challenged and changed. Evidence is the path to truth. The universe is grander and more complex than once imagined. In an age where misinformation and skepticism sometimes cloud public discourse, the story of heliocentrism stands as a beacon of critical thinking and discovery. Ongoing exploration and future questions, the heliocentric theory, while foundational, is part of an ever-growing body of knowledge. Scientists continue to explore how planetary systems form around other stars, the possibility of life beyond Earth, the mysteries of gravity and quantum physics, the large-scale structure of the universe and its ultimate fate. Each new discovery builds on the groundwork laid by heliocentrism, showing how a simple idea can unlock vast realms of knowledge. Conclusion. The sun-centered universe and us from ancient beliefs, placing Earth at the center, to the modern understanding of a vast dynamic cosmos, the heliocentric theory marks one of humanity's greatest intellectual triumphs. It changed how we see the heavens and ourselves. It transformed the cosmos from a place of mystery and superstition into a domain governed by discoverable laws. And it opened our eyes to the boundless possibilities of exploration, knowledge, and wonder. As we continue to gaze upward and outward, the story of heliocentrism reminds us that progress begins with questioning, that truth emerges from evidence, and that the universe, vast and majestic, is there for us to explore. The journey of the heliocentric theory is one of the most remarkable stories in human history. It is a tale of curiosity, courage, and the power of evidence. starting with ancient ideas that placed Earth, and by extension, humanity, at the very center of the universe. The heliocentric model shattered that long-held view and reshaped our understanding of the cosmos. Copernicus's bold proposal, Galileo's courageous observations, Kepler's precise laws, and Newton's universal gravitation together laid the foundation for modern astronomy and the scientific method. The heliocentric theory did more than explain the motions of planets. It challenged authority, inspired the Age of Enlightenment, and changed the way we think about knowledge, reason, and our place in the universe. From the vastness of our solar system to the billions of galaxies beyond, our understanding has grown dramatically, but the core truth remains: Earth moves around the Sun. This simple fact reflects humanity's ability to question, to seek evidence, and to uncover truths far beyond what our ancestors imagined. The heliocentric theory is a shining example of how science can transform our worldview, inspire new ideas, and open the door to endless discovery. As you finish this journey through the history and impact of heliocentrism, remember that the story of science is ongoing, and the universe still holds many mysteries waiting for us to explore. So keep wondering, keep questioning, and keep looking up.